Good afternoon once again. Today we're going to continue our discussion on multiple linear regression. In particular, we're going to focus on regression diagnostics. So far, what we have learned is that one of the most powerful tools as far as regression modeling is concerned is the use of ordinary least squares. Least, L-E-A-S-T, signify there that you cumulate or you compute for the squared residuals and minimize, make sure that it's the minimum value. So based on this minimum value, you have values for your parameters, for your predictors, and this set of values for your predictors will generate the lowest squared error terms, squared residuals. And we say that this is a unique set of parameters. Okay, so this afternoon we're going to, after we compute for the parameters, it doesn't actually stop there. We have to evaluate and do regression diagnostics to see if our model, okay, is really the best linear unbiased estimators. If the parameters, if the coefficients are the best linear unbiased estimators or blue. Okay, so let's load first the packages that we're going to use. We have used Psych before, PaceText, OLSRR, Stargazer. Actually, we just need, why don't we maybe just delete this? Okay, we just need Tidyverse, Broom, LM Test, Sandwich, maybe Stargazer. So let's load this. Okay, could you kindly check your file class? Do you have objects here in the environment? If you have, kindly delete this, then just sweep them because, do you have class? I'm not sure if I share it with you. Do you also have the objects that I created? Okay, yes. Clear niyo muna class. Kindly clear the environment. Yeah, I forgot to clear it. We're going to start from scratch. Okay. All right. So, you know what to do, class? Let's load the wage data set, wage, then read underscore CSV, wage, wage, read underscore CSV. Then we have, what's the name of our data? Wage.csv, I think. Wage dot CSV. Am I correct? Okay. Then let's run this. Okay, so let's check. Okay, so we have our data. We have been working on this data for some time now. Okay, and then from your OLS RR last time, we learned that the predictors of the significant predictors based on a stepwise regression are, so let's model that. Let's summarize, summary. Let's call it just fit1 for our model, and LM, regress hourly wage on education plus tenure plus civ status plus gender, right? Data is equal to age. Right, 1, 2, 1, 2. Okay. So we summarize and then generate this output. Okay. So we have the values of the intercept. Okay, we have here the individual t-tests. By way of review, we said that when you interpret education, it's for every 1 year increase in education, there's a corresponding $0.53 increase in hourly wage, ceteris paribus. For tenure, it's for every 1 year increase in tenure, there's a corresponding around $0.154 dollars increase in hourly wage, ceteris paribus. And then here, single respondents received $0.68 less than their married counterparts, ceteris paribus. And here, male respondents received $1.71 more than their female counterparts, ceteris paribus. So for the overall goodness of fit test, your null hypothesis is, if you recall right, class, our null hypothesis here is that H null is beta 1 is equal to beta 2 is equal to beta 3 is equal to beta 4 is equal to 0. Okay? By the way, we don't include the intercept in our overall goodness of fit test. So the adjusted R squared is 36%, which means that 36% of the variation of your hourly wage dependent variable can be explained by our model using these 4 parameters. Okay, there are 521 degrees of freedom, which is your n minus k minus 1. Okay, n is the number of your respondents, which is 526, minus k, the number of predictors, which is 4, minus 1 to account for the loss of freedom, because we're going to estimate also the intercept. So that's 521 degrees of freedom. Okay, the degree of freedom 1 is 4, which means there are 4 predictors. Degree of freedom 2 is 521, that's n minus k minus 1. Okay, the p-value is practically less than 0.001. So we reject the null hypothesis that our null hypothesis, beta 1 is equal to beta 2, that all of the variables are equal to 0. We reject this. All right. Any questions so far, class? This is just a quick review of what we have discussed before. Okay, thank you. How about the others, please? Okay, good. Okay. All right. Now here, so that you don't have to write it, I gave you a sample summary of the regression model. So let's take a look at this. So this is what we did. We fitted a linear model estimated using OLS. So you can actually pattern for your quiz, pattern this as a summary report of the regression model to predict hourly wage with education, tenure, gender, and civil status, using the formula hourly wage regress on education, tenure, gender, plus civil status. The model explains a statistically significant and substantial proportion of variance. R squared is 0.37, with F, degree of freedom 1 is 4, degree of freedom 2 is 521, is equal to 74.95. Where did we get 74.95? Here. In your F stat. 74.95 with P is less than or equal to less than 0.001. Sorry. Take note that your p-values are stated in 3 decimal places. Okay, the others are 2 decimal places. R squared 0.37, adjusted R squared 0.36. Here. Okay, the model's intercept corresponding to education is equal to 0, tenure is equal to 0, gender is equal to female, civil status is equal to married, is at negative 2.16. Okay, so let's just look at that again. This is negative 2.16, right? Now, the intercept is the average value of your dependent variable, hourly wage, when all your parameters are equal to 0. So education is 0, tenure is equal to 0, Civil status is equal to 0 means what? Plus. If civil status is equal to 0, what does that mean? Thank you, Krisha. You're correct. Yeah, married. Correct. Kasi si married is the reference variable, di ba? Which means it's equated to 0. Single is the one that's equated to equal to 1. Okay? So you only have here one dummy variable because you have two levels. All right, and R defaults into the level that appears alphabetically. The first will be your reference variable. Your reference variable means you're giving it a value equal to 0, while the rest gets a value of, well, if it's only two levels, then the other variable will get 1. However, if you have, let's say, 5 levels, that means you need to introduce, R will introduce automatically four dummy variables. Okay? And then when we interpret this is the light of the dummy variable, of the reference variable. So civil status equal to 0 means that it's married. Gender equal to 0 means it's female. Right? That's why it's saying here in the output where gender is equal to 0 or female and civil status is equal to 0 or married. And the intercept is at negative 2.16. All right, negative 2.16, this one. And then we're given here the confidence interval, 95% confidence interval. Okay, negative 3.43, between negative 3.43 and negative 0.9, with t value equal to 521. Okay, t with a degree of freedom is equal to 521, and that gives us 3.37. So that's our t value, negative 3.37, right? P is less than 0.001. Okay, how did we compute for this? How do we get the confidence interval? Anyone, do you recall your stat? That's important, class. Another way to determine whether our variable of interest is whether we reject or fail to reject our hypothesis. Okay, one way to look at it is through the p-value. Another way to look at it is through the confidence interval. So we're given here the confidence interval. So it's important that we know how to compute for this. This one. Where did this come from? Negative 3.43. Anyone? How do we compute for the confidence interval? Okay. All right, so let me answer that. The confidence interval will be equal to the value of your coefficient. And then since it's an interval, you should be having plus and minus, right? So that's the value of your coefficient. In this case, it's negative 2.16. And then plus minus, you have your standard error multiplied by your t critical. So that's a formula. The confidence interval is equal to b sub I, b. B plus or minus the standard error times t critical value. So in our case, for education, okay, we were told that the intercept had a confidence interval equal to negative 3.43 and negative 0.9. So you notice that you do not have, it's not possible to have 0 here between your confidence interval. You will not have a value equal to 0. Hence, we're able to conclude that that our inference that beta sub 0, which is the intercept, is equal to 0 is rejected. Because based on a 95 confidence interval, it's not possible for 0 to be reached. Okay, negative 3.43, that's the lower limit. Negative 0.90, that's a higher limit. So it's not possible to have 0 there in this interval. Okay, so let's just show that indeed this is negative 3.43 and 0.9. Before we compute for this, we have to know the T critical. Okay, the T critical. We know the degree of freedom to be 521. Okay, we know this. That's n minus k minus 1. N is 526 minus k, which is 4 for predictors, minus 1 to compensate for the degree of freedom lost for computing for the intercept. So that's 526 minus 4 minus 1, that's 521. Okay, so we know the degree of freedom, 521. So we just need to compute for the T critical, and in R, that's very easy. Just use Qt, the Qt function. Let's run that. Okay, here. So this comes from the stats package. This is the T distribution. And what we need is here, Qt. Okay, so what's Qt, class? There's a definition here of our Q, of our quantity. P is the probability. Okay, X. Okay, it doesn't define Qt, but Q is supposed to compute for the critical value of your T, this one. Okay, so let's just copy this, Control C, Control V. You just need two parameters. Okay, P. What will be P? P is the probability. Okay, our level of significance is 5%. However, this is a two-tailed test, so which means we're looking at it from the negative side, left side of your T distribution, and your right side. So our P should be equal to 5% divided by 2. So that's 0.025. Okay, let me put here 5% over 2. Okay, why are we dividing it by 2? Because this is a two-tailed test. Okay, we're looking both at the left side and the right side of your T distribution. And your degree of freedom is, what's N? Okay, that's N row of wage, right? N, how many observations does wage have? Minus, that's how many predictors? 4, right? Or that we can use N call of wage and then subtract 4. Why are we subtracting 4? Because we're not including hourly wage as part of your degree of freedom. We are also excluding the other variables, like race, number of dependents, and experience. So that's why there are only, the number of columns is 8. Okay, 8 minus 4, that gives us only 4. So the degree of freedom is, let me close this in parentheses, N row is 526 minus K, N column, and then minus 1. Okay, 1, 2, 3, 1, 2, 3. Okay, N minus K minus 1. All right, so we get, oops, something's wrong with my formula. 1, N row of range 2, what's wrong with my formula? 1, 2, 3, 1, 2, 3. Okay, N row. Sorry, this should be, okay, N column, okay, that should be there. And then minus 4, and then minus 1, N column minus 4. Degree of freedom is 526 minus 4 minus 8 minus 4 minus 1, and then, sorry about that. All right, so I think this is correct now. Still an error. Where did I have that error? Okay, I remove this. One, two, minus 4, minus 1. Yeah. Oh boy, wait. Let me just, sorry, maybe I'm just low bat now. So let me just use 521. Oh, what happened here? QT, P and then degree of freedom. P is, any comment here?
Baka yung percent,
oo
sir.
nga pala, no? Yeah, tama, you're correct. It doesn't, this should be, yeah, you're correct. 0.05. Okay. 0.05 divided by 2. So this should have been correct, no? The other one. Yeah. 0.05 divided by 2. And column minus 4 minus 1. Okay. Yeah. This should be okay. All right. So the T critical, okay, could have called it T crit. T crit. Let's give it a name, okay, so that we can easily use that. All right. T crit is printed. That's negative 1.96. So when we just to show you how we compute for the confidence interval, where did we get this? Where's the first confidence interval here? Negative 3.34. This is for the intercept. Okay, so okay, the value of our parameter for the intercept is this one. Let's copy this. Control C, Control V. So plus, so this is our standard error, and then multiply that by our T critical. Okay, so we have here negative 3.42. Is this correct? Did it give us negative 3.42? Yeah, okay, 3.43 rounded off. And also for the lower and the upper, negative 0.9. Let's see. So just change this with minus. Okay, negative 0.9. Okay. Okay, any questions about the grouping later na lang, ha? All right. So we have this negative 0.9. Okay, were you able to get this class, the confidence interval? Okay, thank you. All right, so let's continue the summary report. This is a pretty standard way already, class, so that you don't have to invent what to write for the final output at least. So I'm assuming that this is already the final output, that this is already okay based after regression diagnostics. So let's first take a look at the effect of each of the variables. Just give a space here. The effect of education is statistically significant and positive, where beta is equal to 0.53. You can see that beta is 0.53. You notice that when we do the report, it's just 2 decimal places. You don't have to include 5 decimal places. 95% confidence interval between 0.44 and 0.62. Okay, then, so how did we get that? Same thing, class. same thing. So you take a look at the value of your education and then the standard error. So we need the B, okay, the estimate, and then plus, this is your standard error, multiply that by your T critical. Okay, oops, T crit, and that will give you 0.43. So you check there. Where is that? Education, 0.43, 0.44, 0.44, this one, and then 0.62. That will give you, if we subtract this, 0.62, okay, 0.62. All right, T is 5 degree of freedom, 521, and it's equal to 11.27. Okay, our T value is this one. Okay, and then education, P is, notice the P also is written 3 decimal places, 0.0, unless it's 0.01, 1% or 5%, 0.05. Okay, we have another one here, standard beta. Okay, what's standard beta? This value that we're getting, this one, education, this 0.553, this is your unstandardized beta. Okay, unstandardized beta to. How do we interpret this? We learned that this is for every 1 year increase in education, there's a corresponding $0.53 increase in hourly wage ceteris paribus. Okay, so that's the interpretation of your standardized data. In the report, we can give the standardized beta. Standardized beta is equal to 0.4, and then we can also give the confidence interval. So how do we do that? Okay, so let me just teach you how to do that. Okay, let's create this object called fit1 underscore, let's call it S. Okay, fit1 underscore standardized. Okay, alt minus. All right, there are several ways to compute for these standard betas. What happens is that the values that we use is not the original values. You will have to convert education into its standardized value. So for example, before we do that, how do you compute class for the standardized value of education? Let me just print wage. All right, so this is education 11. Okay, that's the first observation. How do we standardize this? You standardize this class by you subtract 11 from the average of education, okay, and then divide it by the standard deviation of education. Okay, so let's just show mean educ. So let's create this object called mean educ, and it's equal to the average of wage education. There. So we're getting the average of education, right? And then let's also get the standard deviation of education, alt minus, which is SD of wage education. So we now have these two values. We have mean and a standard deviation. So when we standardize education, we will subtract each of this from the mean and then divide it by the standard deviation. Okay? You get me, class? So let's see. Let's start with 11. So 11 minus your mean educ, okay, divided by your standard deviation educ. Standard deviation, no, we call it standard deviation underscore educ. That's the name we gave to our standard deviation, right? This one. Okay. So that, oops, mean educ. I'm careless with my It should be min educ. Quite correlates with my variable name. All right, so it's negative 0.56. All right, so you do the same thing for all the variables for all the values in education, and then you regress. So you regress your hourly wage based on the standardized value of education. Okay. All right, so there are different ways to do that. You can create a variable. Okay, for example, I'm going to, let's say, wage. I'll call it wage underscore, just underscore one, okay? Wait, wage. Let's create educ underscore s. So I'm using the wage. I'm creating this column, wage underscore s, all right? And it will be, okay, so you can actually create a function called this one, or just use the scale function. The scale function allows us to standardize the variable itself. Okay, so here I'm creating an object, wage. In wage, I'm inserting this education underscore standard S, let me call it STD, standardized, and it's actually the scale of wage, dollar, wage, dollar, educ, there. So let's see what happens to this one. Control Enter, and then you now have this. Okay, you now have this class. Okay, education standard negative 0.56, right? Negative 0.56. So there you go. Right. So you'll have different standardized values, and then you can use this now as a regression, as your variable to and regress hourly wage on it. Okay, so the value that you will get there is your beta, or your standardized regression coefficient. Okay, so let's now do that. Okay, so let's create this object called fit1. Let's call it STD, standardized. Let's summarize this again, summary. Okay, summary of this one. And then LM. Okay, so let's scale everything. Scale of hourly wage. Regress on scale, education. Let's just regress everything because we will need anyway the beta, the standardized coefficients for so that's tenure. All right, plus civil status plus gender. They are factors. So although you can still scale that, but let's just not scale for civil status and gender, and then data is equal to wage. All right. So we're now creating a model fit1. Let's call it fit1 standardized, where you are regressing the standardized value of hourly wage on education scale. Okay, using the wage data set. Okay, one. Okay. All right. This is okay. So let's print this. Control Enter. Oops, kulang ako, no? One. Kulang ako ng isa pang ano. I lack one parenthesis. All right. So this is, let me redo this. Okay. All right. So what do we have here, class? You can see now that our model was created using standardized values of hourly wage, standardized values of education, tenure, okay, from the data wage. Now, what's interesting here is that the estimate here are standardized values. And how do we interpret this? This is interpreted in terms of standard deviations. So this means that for every one standard deviation increase in education, there's a corresponding 0.4 standard deviations increase in for every one standard deviation increase in education, there's a corresponding 0.4 standard deviations increase in hourly wage ceteris paribus. All right, so you notice that this is 0.4 approximately. Okay, tenure is 0.3. And let's go back to our outputs here. Okay. Let's see what I shared with you. All right. So for education, the standardized beta is 0.4, right? That's 0.4 here. This is 0.4, right? Okay, and then also, you now have this, the confidence interval, negative 3.43 and negative 0.9. All right, so we can compute for that again, okay, but let me show you a secret, a shortcut. Actually, the shortcut is just using the confint. So this function confint gives us the confidence interval. Okay. In fact, we can use this for the model a while ago, but let's use it first for fit. What was our model? Fit underscore STD, right? Standardized. Okay, fit underscore standardized, which is this one. And let's see if it will give us, oops, did I use the right? Sorry, fit one. Fit one, very careless with my names. Fit one standard deviation. All right, you can see here that this is now the standard deviation for education. Okay, 0.33 and 0.47. So let's compare for education, 0.33, 0.47, right? This one. The standard beta we were able to show you a while ago, 0.40. Okay, the 95% confidence interval is 0.33 and 0.47. This one, education, 0.33, 0.47 to the nearest 2 decimal places.
Sir, I have a question po.
Yes?
Is that confit just the same as the formula we used? The beta plus minus SE T crit?
Yes, yes. Oh, shortcut siya. Okay, let's show. Int, the one that we used a while ago is fit1, right? That was our first model, fit1. Okay, so take a look at this. Let me run this. Okay, so for the intercept, what did we get a while ago? Negative 3.43. Is it the same class, this one? Where's our intercept here? Okay. The model's intercept corresponding to, okay, confidence interval negative 3.43 and negative 0.9, right? We computed that a while ago, right? Here. We use the formula. We use a formula, which is your B. Okay. Here, the value of your parameter, your coefficient, plus your standard error times your T critical. So negative 3.43 and negative 0.9. But you can just use the confint function, and it will give you the, so notice this is 2.5% left tail, 97.5% at the right tail. So all in all, 2.5 on both sides at 5, that's 5% level of significance. 2.5%, 97.5%. That confidence interval is 95%. 97.5 minus 2.5, that's 95% confidence level, confidence interval. Okay, did that answer your question? Who is that? Stephen, ikaw ba yun?
Yes,
Yeah, did that answer your question?
yes, sir.
Okay. All right, let me pause for a while. Any questions, class? So all of this, class, you can compute. Okay, you can easily compute this. So there should be no reason why you should not be able to generate this report. Okay, so here the effect of tenure is statistically significant and positive. Beta is equal to 0.15. Okay, of course, class, when you're suppose you're going to include all the variables. Okay, so you have your final model. Okay, where you did stepwise regression, but you will of course include those variables that are not significant. So, kasama sa report kasi yun di ba? If you were using, let's say, 7 predictors and only 4 were significant, then you will also have to report the 3 others that were not significant. Okay, so kasama din siya dito, no? The effect of, let's say, race is statistically insignificant. Okay? And then, of course, pwede naman masama, no? Yung mga sa confidence interval na makikita natin that it will touch 0. Kaya siya hindi naging positive. Okay. All right. So let's check this. For example, si male, statistically significant and positive beta is 1.71. You also have your confidence interval, which we can see here. Dito si male class, 1.19 and 2.23. So dito siya, 1.19 and 2.23. Tapos yung standard beta niya, 0.46. It should be here. Si male, 0.46. Ito, no? Yung standardized beta niya, this one, 0.46. And then confidence interval, 0.32, 0.60. So does it give us the correct confidence interval? Si male, 0.32, 0.60. Okay? So everything is good. We were able to show the values here where they were coming from, and you can of course generate that from. For the standardized beta, you have to run your model using the scale function. Okay, of course there's a faster way to do that. This function, the scale, what we did a while ago, this one. Okay, so let me copy this just for record purposes. There, Control C. Scale. All right. I will leave you guys to check what would happen if you also scaled civil status and gender. Would there be a difference? All right. So there are also okay. There is a package called performance. Okay, we're now going to multiple for regression diagnostics, and there are some very important packages that we can use as far as regression diagnostics is concerned. I have mentioned to you a while ago yung LM test, yung Brooms package, yung sandwich package. I failed to include there the performance, so kindly load the performance package. If you don't have it, then you install it first. For me, I have it already. So I'm going to load the performance package. Kindly load it. Then once you have loaded it, we will check. Okay. We will use some functionalities coming from the performance package. Okay, please check if you have loaded the performance package. Okay. About the others, please. Okay, let's give your classmates a few more seconds. Not even half have already confirmed that they were able to load the performance package. I leave you guys to study the documentation, what performance package does. Okay, so just a quick, while your classmates are still loading it under packages. Okay, let's put here performance. So what does this do? Assessment of regression models performance. Okay, so there are several packages here. I'm sorry, there are several functionalities here. Okay, you can check for here, check outliers. Okay, check heteroskedasticity. Okay, isn't it that's what we're going to use? Isn't it that's what we're going to look at this? Look at as far as our model is concerned. Okay. All right, so let's first check this. Let's use this model underscore performance. Okay, this one. All right, so model underscore performance of our FIT1 model. Okay, and then it will give us some summary metrics. Okay, we have the AIC. This is the corrected AIC, VIC, R squared, adjusted R squared, Ramsey, root mean square error, and then your standard error. No, performance analytics is different. Performance lang. Performance analytics is used for investments. Okay. I think some of you are my students in FinAnli, so we're using financial performance analytics. But here it's just performance. All right. So aside from that, if you take a look at, we can now check also here. There's a function here called okay. It's a class, no? Here. Check model. So let's use that. It's a visual check of model assumptions. Right. So this is a pretty powerful model also. Check underscore model of FIT1. So we're asking R to check the FIT1 model, and it will give us some plots here. Okay, and I find running it here better. I'll run the function here because it's not, I can't see it so much here. So let me run it here. It's better to see here it under the plots package, plots portion. Let me run it again. Taking some time. There, class. Hello, class. Can you hear me?
Yes,
Yes,
sir.
sir, we can hear you.
Okay, sorry. Can you see the message here?
Yes, sir.
Nag-abort sandali. Ay, sandali. Sorry about this. Let me start. Ay,
No worries, sir.
ha?
No worries po, sir. Okay.
Sorry Siguro napagod na si R. O empty na naman siya. So, let me open. Yeah, this is now the importance class of having a project. Kasi, kung wala tayong project, tapos we were working on that file, wala na. Wala na yun. Hindi na ano yun, masisave yun. So, gone forever. No? So, buti na lang I saved it dito sa, okay, where's this? Let me just check. So our project FINTSAR multiple regression, and okay, I'll go here. So dapat, okay, but it did not open the project. So better class kung better kung ang inopen ko dapat yung ano. Okay, let me open the project itself. Ito class, multiple linear regression project. Kasi kung yung file lang inopen ko, tapos pag if once again nagkaroon ng problem, baka tapos hindi ko siya na-save, then hindi masisave yun. No? Unlike kung ang buksan ko yung project mismo. So this is the project itself. Okay, so wait lang. Okay, it's opening. Okay, there. So I open the project, and then for the files, kita nyo, ito yung project, no? Multiple linear regression. Okay, ito yung files. We were working on this a while ago. Diagnostics1. Okay. Okay, take a look class, no? Di ba nagsara na ano sa kanina? Pero, what we did, still saved here. Yan, no? Ito yung last na ano natin. Yung check model fit. So, it's here. So, take it from me class because I've experienced that several times before, long before. Hindi ko sinisave sa project as just as an individual file. Tapos when something happens, nawawala na yung file na ginawa ko. Dati nga more than I think 900 lines of codes na yung nagawa ko. Tapos talagang I really cried that time kasi several weeks kong ginagawa yan tapos biglang nawala. Stupid me, hindi ko sinesave. No? Ayun, everything gone. All right, anyway, so let me run it here, check model fit1. Okay, ano nangyari? Could not find the function. Kasi, yun, you have to load again the packages. Sama ko na dito si performance. Performance. And then let me load it. Okay, and then here. Nawala kasi ano ko, no? Nawala na class yung mga objects ko dito eh. Okay. Yun. At least, yun ang isang ano. Okay. Nag-abort kasi siya, no? Hindi na. Anyway, I'll just run it, class. This one. Okay. I need to run also our FIT1 model. Okay. And then I think that's enough for us to be able to check this. Okay. That should run. May FIT1 na ba ako? Yan. Okay. So zoom ko lang. Okay. So we have some pretty important information here in this plot coming from the performance package. Okay, first you have here you have a plot of your residuals and superimposed on a normally distributed distribution. It looks like your residuals are not normally distributed, and that can also be seen here in our QQ plot here. In our QQ plot, it indicates that I can, of course, export this. But never mind. Wag na muna. No? Aside from that, we also have we have here linearity, homogeneity of variance, influential observations, collinearity. So these are what we need to test the assumptions of our model. We have the assumption for multicollinearity, that the independent variables should not be multicollinear. So as far as that is concerned, we seem to not have a problem because the standard use is the variance inflation factor should be less than 5. So here we have the variance inflation factors relating the variables among each other is less than 5. So no problem as far as multicollinearity is concerned. Here you have this square root of the standardized residuals. Okay, so you know how to get the standardized residuals. You have your residuals and then you just scale them. You scale them. You subtract it from its average and then divide it by its standard deviation. So it looks like indeed our variance, our residuals do not have constant variance as shown by our plot here. Okay, there seems to be a pattern. Seems to be a fanning out of our residuals, which means that as we increase the treated values, our residuals are also increasing. However, for influential observations, there seems to be no problem. Now, next meeting, we're going to discuss the difference between outliers, leverage points, and influential points. Okay, that's a very important thing because influential points are observations that affect the values of your parameters, the values of your coefficients. Okay, all right. So these are very critical plots that we can use. In your first case class, you have to use this. But please do not just give me a plot. Okay, you have to analyze because that's what will get the points, not the plots. Because the plots, you just write this one function, check model, fit one, then voila, you have the plots. Okay, that will only give you around 2 points but the rest of the 28 points will come from your analysis. Okay? All right, so let's continue. Now, this is our regression diagnostics. I have some notes about this one. So we don't just, I leave you guys to read some of this. We don't just do the modeling. We don't just determine what are the values of your parameters. We have to check and to test whether our model violates the assumption. Our model violates the assumptions of our classical linear regression model. So what are the assumptions? Let's have a quick review. Number one, linearity. Okay, when we say linearity, okay, the outcome y is a linear function of the predictors. Now, again, class, it doesn't mean that x should be x cannot be squared. The linearity here underscores more your beta. Your beta should not be nonlinear. Your beta, your coefficient should be, it cannot be squared, it cannot be cubed, it cannot be square root. But for our x, okay, our predictors, it can be squared, it can be cubed. Okay, because if x was cubed, you can just replace it by a function of x. Let's call it x star, for example. Okay, so you're able to convert your x, which is x squared, into a linear function again. All right, and if there's linearity plus, what happens is that this one, the expected value of your residuals given your x values is equal to 0. Okay, so this is very important. The implication of linearity is that the expected error, which is based on your condition on your x, is equal to 0. So that's how that is written. Also, your homoscedasticity, okay, which means that the variance of your residuals given your values of x, given your predictors, should be constant. Okay, so for this one, the residuals should not be related to each other. The residuals should not covary. Okay, so the covariance of your epsilon sub I and epsilon sub j, which are your residuals given x, they should be 0. They should not be correlated. And also the normality. Your residual should follow a normally distributed. Should be normal distributed with mean 0, which is consistent with this one. Okay, this one. Wala. Ito. Huh? Consistent with this one. Expected value of your residuals is 0. Mean is 0. And then constant variance. Okay. The other assumptions include, as I mentioned a while ago, no multi-collinearity among the independent variables. Outliers, we're going to look at it next meeting. The file that I gave you, I also sent 4 files, Excel files. Kindly look at them. We're going to study the outliers using those files. Okay, no measurement error, specification error. We'll also go into this. In fact, let's first go into linearity and specification error, which is quite related to each other. Okay. All right, so let's take a look at this. We plotted the model a while ago using the SEC model. Another way to do it is use the plot function, plot fit. Okay, so let's do this. Okay, sorry, I'm rushing a bit so that we're on the same page as the other section. All right, sorry, fit 1, this should be fit 1. All right, so this is the plot. It gives us 4 plots, but actually there are 6 plots here. Okay, so this one is your residuals versus fitted values. And we discussed before that we would want the residuals to exhibit a constant constant variance over the values of your fitted values. Here it seems that your residuals have greater variance as the fitted values increase. Okay, so you can notice here a fanning out, spreading. At this part, your variance is greater compared to the variance at this point where you have lower fitted values. Okay, then we also have this. This is your normal QQ plot, which is the same as the check model. Okay, this tells us if our residuals are normally distributed. Then we also have this scale location. It's similar to the check model also. Square root of the standardized residuals and the fitted values. And then this last one is your residuals versus leverage, right? Which we don't find in the check model. So if you want class all the plots, so plot and then fit one, we can identify which is equal to 1 up to which is equal to 6. Okay, so let me just copy this. Okay, no, never mind class. This will give us the first plot. Which is equal to 1 will give us this one, right? This is the residuals versus the fitted values. Which is equal to 2 will give us the QQ plot. There, so QQ plot. Okay, which is equal to 3 will give us the standardized residuals. There, square root of the standardized residuals. Which is equal to 4 will give us a different plot which you do not find in plot fit 1. This is your Cook's distance. Okay, here. The Cook's distance is a measure to determine what are the influence points, potential influence points. So you have here observation number 112, observation number 59, observation number 260. We're going to take a look at this next meeting. And then which is equal to 5. Okay. This is similar to the number 4 of what we here. And we also have number 6. So there are 6 plots actually. All right. So this is Cook's distance versus leverage. So we're going to take a look at the difference between Cook's distance and what does leverage mean. Okay, if you want to see all the plots together in one, okay, show us one plot, we can make use of the partition function. So you have par, which means partition, and let's identify the number of rows. C is 2 rows and 2 columns. Now, and then we write the plot fit 1. Okay, now this will give us a plot that includes 4 of the plots. Okay, so it includes the 4 plots which you can find in plot fit 1. Okay, even if you increase the number of rows and columns, for example, this one I'll make 3 by 2, which means that hopefully it can include the other 2. Okay, because there are 6 plots that are shown. However, if I run this class, it will only give us, okay, it generated 4 rows and 2 columns, but it did not give us the other 2. Incidentally, class, if I type here is equal to 7, it will return an error because there are only 6 plots that the plot of the model give us. All right, so I will leave you guys to go over this. Please read what this residuals versus fitted, the normal QQ plot, the scale location, residuals versus leverage, and please take a look at what the Cook's distance does. And also there are other measures called DF fits and DF betas. Also do a research on that. There's also this autoplot function, okay, which will just give us the same. However, you will have to load first ggplot2, which you have loaded already when you loaded the tidyverse, and also sometimes gg45. So if you don't generate this, okay, so na naman ako, no? Autoplot, sorry, not, yeah, autoplot fit 1. Okay, So sometimes it runs, sometimes it doesn't run. So what I do is library GG45. I load GG45 also, but autoplot actually comes from ggplot2. So I'm wondering why the autoplot does not load if I've loaded ggplot2. Okay, just the same class, only that this looks a bit better. Others prefer this, while others prefer the regular one. Okay. All right. So I have only a few more seconds. So for those of you who need to go, you may go. I just need 1 or 2 minutes just to finish this. Okay. Now there's this function called augment. I'll put here fit1, and then our diagnostics. Let me call it fit1 diagnostics. And I'm going to use the augment function coming from broom. Okay, so let me put here broom. Okay, and then fit1. All right, and then let me also, okay, let me just automatically view this. View fit1 underscore diagnostics. All right, so what do we have here? The augment function in Broom allows us to add on to the variables of interest in fit1, which are hourly wage, which is your dependent variable, and your 4 other variables, regressors, predictors. And then you have here your fitted value, your residuals, hat values. Okay, I'll explain this next meeting. What are these dot hat? And then this dot sigma. Okay, this is your standard errors. Cook's distance, which is used to determine if a particular point is an influential point. Remember, you have 15. 15 is the Cook's distance is 0.003. Okay, so it's quite higher than the others. Okay, you also have 112. If you recall the drawing class, so no, ito 260. Sorry, 260, 59, 112. If you take a look at, you can sort this. Okay, you look at 59. What's 59? 59 is, yeah, it's 0.007. Okay, the Cook's distance. So it's relatively higher than the others. 59. How about 112? 112 is, okay, so 112, sorry. It's 0.08. It's higher than 59. And the other one is, what's that one? Is it 260? Observation 260. Okay, it's a bit lower, but it's 0.045. All right, so okay, next meeting, we're going to continue with this. Okay, kindly look at the Ramsey regression equation specification error test. This will test whether our model is sufficient, or is there a need to put squared values of your excess? Because what we did was just to regress our hourly wage on education and tenure. So will a squared value of education be better? So should we now make it hourly wage regress on education, education squared, education cubed, tenure squared, tenure cubed? Okay, so we'll discuss that next meeting. All right, so that's addressed by the actually that's addressed by the specification of our model. Okay, this one. Number 8, specification error, or we can call it omitted variable bias. Okay, so with that class, we call it today. Thank you so much. Let me stop recording.